not be used. Should be used some more difficult differential equation. There, these things will not occur because that is a totally different approach. So therefore, we should realize that all conclusions that I get are based upon linearized theory. All conclusions are based upon this idealized, linearized theory. You see, since you asked me this question, I will use more paper and nine. Actually, what happens is as follows. Look, please. This is value of P. And that is some characteristic of displacement. This is 0. Then what we get actually is as follows. Until this critical value, P critical, displacement equals 0. So this curve is like this. But at P equals P critical, so to say, displacement can go that way or this way. So this is called bifurcation or branching. Okay? So some systems behave like this. Some systems behave in different manner. Okay. I'll give you 3 cases. So these are all critical load. Okay, so this is P, this is P, and this is P. So some systems behave like this. Look. So look, that is here, and after that it goes there. That is nonlinear behavior, nonlinear. Here, then this one. Okay, so that is this. And thus, some systems could behave like this. Now, these are all idealized systems. Okay, why don't you make these pictures? Forget now displacement of the top. Displacement, some displacement. Oh, okay. If we talk about simply supported columns, then we mean, of course, middle displacement or displacement anywhere. Before that, for example, this was like C3. Do you remember, everything except C3 is 0. So this would be coefficient C3 for that column. But here, I'm talking about, forget now, just displacement. Just imagine displacement, because I did not give you a problem, so you cannot ask me what kind of displacement is there, because I didn't. That is a generic behaviors. No, this I said systems. I did not say column. I did not use the word column. Okay? Or you may want to think, say, displacement in some point, if you want to think. Now, this is how system behaves. But now, in reality, columns are, columns are never straight. Reality. Never straight. So therefore, there is some initial deflection. initial deflection. Then in the realistic system, pay attention, that is how system behaves. That is as a response to the question. Otherwise, I would not talk about this. So reality is given by the dashed lines. Now, pay attention. In reality, then, there is no bifurcation. Pay attention. This bifurcation is character. What is this bifurcation? Branching, like here. Pay attention. There is one branch, there is a second branch. So this is a bifurcation point, okay? Here in each of our hands. We see the bifurcation point here between these two fingers. So ideal system has a bifurcation that is in this point. So that is a bifurcation. Pay attention, there was one equilibrium, then there are two. One equilibrium, then two, left or right. One equilibrium, or here, there, or there. But in realistic system, there is no such a thing like it goes or here or there. This goes or like this or goes like that. Okay, but that is much more difficult nonlinear theory. Nonlinear theory gives more insight, so to say. But this is a fascinating topic, naturally. Covered in the course Theory of Elastic Stability. Okay, I'm giving a course that is totally devoted to stability whole semester. So there are linear systems, nonlinear systems, including something. So this is called theory of imperfection sensitivity. Okay. Theory of imperfection sensitivity. Any questions? More questions? Okay. Now we found buckling load. Okay, now we will go to that 20. Topic 20. Natural frequencies of the column under axial load. Okay, so that will be number 20. And here we deal with our column. There is P, and there is P. Now, this P is not necessarily, P is arbitrary. Not necessarily P critical. But this vibrates. What we did before was static consideration. There was no vibration. We did not, it is not on the base of vibrations or something. So now our differential equation will be like this. EI d4w dx in force power plus P d2w dx squared plus rho a d2w dt squared equals 0. Okay, now w, small w x of t, can be written as capital W of x cosine omega t. Pay attention, I specifically wrote this omega in such a manner that it is difficult to mix with w. I substitute and I get ei d for capital W dx in fourth power plus p d2w dx squared minus rho a omega squared w equals 0. We want to find omega squared as a function of p. So that is what we want to find. Okay, now w, let us check w. W, let us take it as some constant, c, times sine n pi x over L. Because it satisfies boundary conditions. This function satisfies boundary conditions. Indeed, w, okay, excuse me, at x equals 0, w equals 0. Yes? When sine of 0 equals 0. At x equals L, w equals c sine n pi, and therefore it also equals 0 when this x equals L. Then, second derivative, of course, equals minus c n pi over L squared sine n pi x over L. So second derivative at 0 equals 0, because sine function. And second derivative at L also equals 0, because there is sine n pi n pi. So function and second derivatives equal 0 at 0 and L. So boundary conditions are satisfied. So therefore, we can substitute this into here. Sorry. It's into there. And we get. So ei c fourth derivative n pi over L in fourth power. And then with sine n pi x over L. And plus p, but second derivative, minus p n pi over L square sine n pi x over L. Minus, and then c, of course. Minus rho a omega square c sine n pi x over L equals 0. Okay, this is what we get. So c sine n pi x over L can be taken out of every expression. What is left is ei n pi over L in fourth power minus p n pi over L squared minus rho a omega squared equals 0. So again, C is not 0. So this should be also valid for every x. So what we have is EI. So therefore this parenthesis should 0. N pi over L in fourth power minus capital P n pi over L square minus rho a omega square equals 0. And we get omega squared. Omega square equals EI over rho a n pi over L in fourth power minus P over rho a n pi over L squared. So we are interested, of course, with n equals 1. So that is, therefore, it is n's frequency. Or maybe I better write, sorry, here I will write omega n squared. It's a definition. So we get therefore omega 1. Omega 1 squared equals EI rho a pi over L in fourth power minus P over rho a pi over L squared. So we see as follows. When P equals 0, omega 1 squared equals EI over rho a pi over L in fourth power, our familiar equation, familiar expression. Okay. Now, omega, so if we make a figure, that is omega 1 squared, that is 0. And this is P. So naturally, this is a linear function. It's a linear function. Linear function of P. Question: at which P does the first natural frequency become 0? This is a question. At which P does the first natural frequency become 0? Say it again. We will see. Now we will write omega 1 square equals EI over rho a pi over L in fourth power minus P over rho a pi over L squared equals 0. So this can be denoted actually like some, okay, this goes straight. So that is this value. You Okay, P sub 0. Let's call it P sub 0 because omega 1 is 0. So that is P sub 0. So then we see that this P sub 0 equals EI over rho A, pi over L in fourth power, divided pi over L square, and 1 over rho A. So this and this and this cancel, and we get pi square EI over L square. So this is nothing else but P critical. Wow, I think it's very interesting. It's very interesting. At the buckling load, natural frequency becomes 0. You may want to write down. At P equals P critical or buckling load, natural frequency equals 0. So then the figure actually is like this. Omega 1 squared, that is P, so that is P critical. And what is this value? We can denote it like this. We can denote it omega 1P squared. P, that means that P is not 0. P is present. Load P is present. Okay, then this value will be omega 1 0. Okay, so this one is omega 1P squared variation. So what we can do is as follows. Pay attention at this equation. This one is omega 1 0 squared. So I can write down omega 1P squared equals omega 1 0 squared minus, and then this divide P rho A pi over L squared. Pi over L squared. Or I can write down omega 1P squared equals omega 1 0 squared, and here I will write 1 minus. And here I will get P over P critical. Or omega 1P over omega 1 0 squared equals 1 minus P over P critical. Very nice formula. And therefore this will be like this. Omega 1P over omega 1 0 squared. This starts from 1. Because at 0, when P equals 0, this is the same. And this is P over P critical. So this is 1. So that is what happens for simply supported beam or simply supported column. It's a nice expression. I don't know who did this first time. Any questions? Yes? Yes. Okay. So the question was cancelled. Any other questions? So pay attention. Somehow the circle of today's discussion closed. From which point of view? Today, so it is a self-contained lecture from the following consideration, methodologically. We started from free beam. We found that free beam possesses two zero frequencies. So one corresponds to translation or rigid movement, and the other corresponds to the rotation. Then here, for the beam under axial load, natural frequencies, as we know, for simply supported beam, we showed past time, do not equal zero, unless this beam is under axial load. If it is under axial load, and axial load equals to critical value, the natural frequency is vanishing. What is the physical meaning of this? Physical meaning of omega 1 p goes to 0 when p goes to p critical. Meaning is very simple. Omega goes to 0 means period goes to infinity. Is it right? That means that a beam returns to its original position in infinite time, or never, meaning instability. Okay, if system does not come back, remember we talked, that is how we started. We give a kick to the system. Then we remove the kick, system comes back to the original position. But period equals infinity means that it comes in infinite time or never comes to the original position, which implies buckling. So therefore everything is in one package in a nice manner, because stability definition and vibration definition yield the same results. We get the same conclusions from buckling and from vibrations. Therefore, many people do something that is called 15, non-destructive evaluation of buckling loads. What does that mean? We don't want, to buckle this column, and column does not come back to the original position, and therefore it remains bent. Then we don't use the column. We cannot use it in a second experiment. But if I will write down omega 1 p over omega 1 0 squared, and here p over p critical, then on this scale I can have experimental data here. So this is an experimental data. And then, so I can just extrapolate and find where this 1 is, and that would give me the p critical. So this is extrapolation. Any questions? So sometimes indirect knowledge allows us to find something that we are looking for indirectly. We get buckling load indirectly as a result of this extrapolation procedure. Okay, if there are no questions, then now we are done for today. Say it again. No, these experiments give us these 3 points, or 2 points if you want, and then you continue, you get the buckling load here. Thank you. Very early, 57 Wednesday, but that is, we don't meet until Monday. And I would like you to have the weekend. Is there anyone who wants these pages?